Hello, welcome to a new mathematics lesson. Today we are going to demonstrate what is the formula to calculate the curvature of a given function. In this case, we are going to work with a function of one variable, y equals f of x. And what we wonder when we speak about the curvature of this function is what is exactly the radius of the circle that covers the function. I mean that if we look to a little piece of the curve, so for every piece of curve, we can attach to each point of the curve a circle, right? And the radius of that circle will be the curvature of the curve at that point. I mean that, for example, at this point, we can think that there is a circle that passed by the curve in this manner, maybe. And then we wonder what is the radius of that circle. So that will be like the curvature of the function at that point, right? So this will be like the point x comma y, and it has a curvature associated to it. Okay, perfect. So we are wondering what is the formula to calculate that curvature for any function f of x. So to show what is that formula, we are going to help us with a draw. So we are going to think that we have a curve, maybe in this way, and we are going to look to 2 points of this curve, maybe this and this, and so that this is an arc of the curve that we are going to think that it comes from a circle, right? Looking that we are just looking to a small piece of the curve, we can think that, well, we have a circle attached to this piece of curve. So we know that, well, we can generate this piece of circle given by a specific angle and a specific radius. Let's say it is rho, and let's call this angle maybe delta theta, right? Okay, so we can think what is the tangent line to each point of this that we have here. Maybe we can set that this is the tangent line whose slope is going to be given by the derivative of the curve, right? If this is the curve y equals f of x, then we know that if this curve is tangent to that point, then the angle that it makes with the horizontal axis, well, it can be equal to a given angle, maybe theta, right? So theta will be equal, actually, the tangent of the angle, right? So tangent theta is equal to the derivative of y with respect to x, evaluated at that point. Okay, and we can do the same thing with this point, where we draw the tangent line, and then, well, this tangent line is going to be is going to have a slope equals to, well, theta plus delta theta, right? Recall that looking that these lines are making a 90-degree angle with this radius, and this also is making a 90-degree angle with that radius, we can say that, well, the difference between this first angle and this second angle is just delta theta, just by looking to the image and looking that, well, this angle is equal to delta theta. Okay, so we know that there is a famous relation between the angle, the radius, and the length of this arc over here, which is ds equals rho d theta, right? This is for a circular geometry, remember, where ds is going to be a differential element of the arc. This will be ds. So I can think maybe in a better draw in an infinitesimal way to see this expression. Maybe this will be d theta, then this will be rho, and then this is ds. So we have the ds is equal to rho d theta. Okay, but again, if this is an infinitesimal portion of arc, we can think that, well, the derivative of the function evaluated at that point, well, is going to be equal to the tangent of the angle, right? So we can think that there is a tangent line passing through this point whose slope is theta, so that the derivative of y with respect to x is equal to the tangent of theta. Okay, perfect. And we are going to see this as y prime. Okay, so we are interested in finding a formula for rho in terms of y prime, maybe y double prime, and so on, because the information that we have is the shape of the curve, right? We are given with a function y equals f of x, and then we want to find rho in terms of that information that we are given. That's only the function y. Okay, so how are we going to do that? Well, from this expression, we see that we can express rho in terms of, well, the derivative of s with respect to theta, right? So we are going to be interested in finding an expression for ds and d theta in terms of y. Okay, so for example, let's say that we have a piece of curve ds, maybe, and then, well, this corresponds to the function y equals f of x, but we are just looking to a piece of arc. And then, well, this piece of arc has an horizontal part and a vertical part, right? Where this can be seen as maybe delta y and delta x, right? So that, well, we can think that there is a hypotenuse that is almost equal to the element of arc ds. But we can establish the relation ds squared equals dy squared plus dx squared, right? And we're going to be interested in taking these intervals as small as possible in an infinitesimal way to take the derivative of the function with respect to x. So we can see from here that delta s is equal to the square root of delta y squared plus delta x squared. And then we can factor maybe delta x so that we can get delta x squared, so that we get delta y over delta x squared plus 1. Yeah, like this. And if we see this in an infinitesimal way, like I mentioned, just by taking the limit as delta x goes to 0, this can be seen as a ds equals to dx, the square root of 1 plus y prime squared, right? Okay, so yeah, with this, we have found an expression for this ds that we need. Okay, and to find the expression for d theta, we are going to use this one over here, y prime equals tangent of theta. So let me write that here. And how are we going to do this? Well, I think that it will be a good idea to take the derivative with respect to x and use the chain rule. So we are going to get that the derivative of y prime with respect to x is equal to the derivative of tangent of theta with respect to theta times the derivative of theta with respect to x. Okay, so this is just also the second derivative of y with respect to x. And then the derivative of tangent of theta is equal to secant squared theta. And then the derivative of theta with respect to x, which is equal to 1 plus tangent squared theta and times d theta dx. And well, we know that a tangent of theta is equal to y prime. So we have something like 1 plus y prime squared d theta dx. Perfect. So I think that this expression is equivalent to say that the element of the theta is equal to y double prime divided by 1 plus y prime squared dx. Okay, so I think that with this, we are able to construct the shape of rho. Again, looking to this formula over here, we know that rho is equal to the derivative of s with respect to theta. So ds is equal to this thing over here. So we substitute that to get dx and the square root of 1 plus y prime squared, and then divided by, well, d theta, which is equal to y double prime divided by 1 plus y prime squared, and then dx over here. Okay. And then let me make some space over here to get that rho is equal to, well, the square root. Actually, it will be, yeah, 1 plus y prime squared to the 3 halves, and then divided by y double prime, and then something like dx, but you know that this is equal to 1, right? Perfect. So with this, we have the expression of the curvature of a function y equals f of x at any point. Recall, if we have the function in the plane, maybe, we can find this value of rho for every point on the curve. So if we are given with the function f of x, we calculate the first derivative and then the second derivative. We substitute in this formula over here, and then we evaluate at the point we are interested in. Okay, so it's not the same to calculate the curvature at this point or at this point or at this point, of course. Perfect. So I think that this is the final result of the lesson. Thank you so much for watching.